Welcome back to all of you. So, we were discussing about stress path, and in the last lecture we have seen stress path for drained triaxial testing. So, in today's lecture we will see the stress path corresponding to undrained condition or undrained test. Okay. So, what is the essential difference? We know that from the shear strength discussion, the essential difference would be in terms of pore water pressure generation. So, we will see how that is going to impact the stress path. So, just like what we have done for drained compression test, there are 4 cases that we discussed here. The first case is undrained compression test with constant radial total stress. Now, when we discussed about drained stress path, we did not have to stress too much on effective or total, but now it is important. So, you can see here that it is with constant radial total stress, okay, and that is designated by U1, earlier it was D1, but the conditions were same. The first condition we dealt was constant radial stress, but here we have specified total stress. So, it is very clear that the TSP and ESP will not be same for the case of undrained test. Just like in normal triaxial testing, we always have the initial condition to be isotropic. So, let us start with isotropic condition M, and again we will discuss for the 3 stress paths, one for in axial radial, the other one is for TSS dash and other one QPP dash. So, this is the starting point, the isotropic condition. So, M is the starting point, like that we have for TSS dash and QPP dash. So, this is the starting point. Now, for the first condition we know the radial stress is constant. So, delta sigma r equal to 0. And for creating compression we know that the axial stress should increase. So, delta sigma a equal to plus delta sigma a. Now, you are more or less conversant with these usage. So, when there is release it is negative, and when there is loading or increase in load it is positive. Okay, so, this is the starting point. Now, for this particular condition we know that TSP remains constant with radial and it increases, that is axial load increases. So, this is increasing in this direction. Now, this is very much similar to the drained triaxial stress path for the same condition. So, the total stress path in both the cases for the drained and the undrained is not going to change. Okay, but you may be wondering, why did I stop this total stress path at this particular point? Why it is so? And there is a discontinuity here. In fact, when it comes to undrained testing, you will see that total stress path will not represent what it actually has to represent about failure. So, it is all governed by effective stress path. So, whether it is complete or not, whether the total stress path is meeting or whether it is crossing the failure line, it hardly matters. Now, let us say that for this particular condition initial pore water pressure U0 exists. What is the implication of this statement? It means that the total stress path and the effective stress path will not start at the same point. So, there will be a difference of U0. So, let us find, so there is a difference of U0 and that remains isotropic. So, the point M will get shifted to M dash for effective stress path. So, that is why it is called M dash, okay, for effective stress path. Now, is it straightforward to plot effective stress path with the given information? But ESP will be separated from TSP by pore water pressure at any time. So, it is an undrained test. So, for every instant the pore water pressure changes during shearing. So, we need to understand what we need to get, what is the value of pore water pressure with loading. How do we do that? Either we measure it, get the results, and you plot the effective stress parameters, the variation, or U is estimated by Skempton's pore pressure equation. Now, you will again appreciate why we have studied Skempton's pore water pressure equation in detail. So, in the absence of measurement, one can also have some idea about pore water pressure by estimating it corresponding to the change in stresses. So, delta U is equal to B into delta sigma 3 plus A delta sigma 1 minus delta sigma 3. So, here replacing sigma 3 sigma 1 by sigma r and sigma A, we have delta U equal to B into delta sigma r plus AB into delta sigma A minus delta sigma r. It is a saturated case, so B is equal to 1. So, delta U is equal to delta sigma r plus A into delta sigma A minus delta sigma r. Now, this is a typical case of delta sigma r equal to 0 and delta sigma A equal to plus delta sigma A. Substitute this into pore water pressure equation. We will get delta U is equal to A into delta sigma A plus delta sigma r 1 minus A, that is by rearranging, and for this specific case delta sigma r is equal to 0. So, now we have delta U is equal to A into delta sigma A into delta sigma A. So, as sigma A changes, the pore water pressure will change. Once we know the pore water pressure parameter A, then we can always determine what is the change in pore water pressure. So, now it is easy to plot ESP, but is it that easy? When we have got the pore water pressure estimated. So, now you can find out what is the effective stress. Delta sigma A dash is equal to delta sigma A minus delta U. We have the expression for delta U. Substitute that, we will get delta sigma A dash is equal to, take delta sigma A outside, 1 minus A. So, delta sigma r dash is equal to delta sigma r minus delta U. Delta sigma r dash is equal to 0 minus A delta sigma A. So, delta sigma r dash is equal to minus A delta sigma A. So, the slope delta sigma A dash upon delta sigma r dash is equal to minus 1 minus A by A. So, you divide this by this, minus comes 1 minus A by A. So, now we are left with an equation for the slope. Earlier it was a number, so it is not changing. Here it changes, the effective stress path keeps changing with shearing, and that change will be with respect to the parameter A. So, ESP varies with A. So, and A is dependent on stress history. This much we have already seen in our previous lectures. Now, consider a case of normally consolidated, because once we have stress history coming into picture, let us first see what happens for NC. Now, let A at failure AF is equal to 0.5 as approximate value for NC, this we know. If A is considered constant, then ESP will be a straight line. So, we have an expression in terms of A. Now, let us say that we assume that A is constant and we take the final A value. This also we have seen A value at failure, that is AF. Now, let us say AF is equal to 0.5 for NC, then we approximate it by a straight line. But if we presume that, okay, let us first discuss what happens when A is equal to 0.5. So, it will be always negative, because it is minus A upon, in the previous slide we have seen the slope which is minus of 1 minus A by A. So, if you substitute 0.5, this will be positive quantity with a negative sign. So, the slope will be negative. So, this is the negative slope which you can see, and M dash N dash represents the effective stress path for a value of, let us say, AF equal to 0.5. And in reality, that is for a case, this straight line is a case when AF is equal to 0.5, that is considered to be constant. but A changes with shearing, and hence the effective stress path will be non-linear. Every time it keeps changing. So, if you consider the variation of A with respect to shearing, then it will be more like a non-linear change or non-linear effective stress path. But most of the practical cases that we discuss, we consider A value to be a constant and we take the value of AF, and hence we can consider the effective stress path for undrained condition also to be a straight line. So, the same thing that we try to do in TSS dash plot. Starting point is there, delta sigma r 0, delta sigma A is equal to plus delta sigma A, everything remains same, u naught exists. So, then it will be shifted. Now, this also we have already seen in our initial stress path discussions, like S naught dash will be S naught minus delta minus u naught. So, in case if you have any doubt, please refer back to the earlier lectures. So, this is the point M dash. Okay. So, it is separated by initial pore water pressure u naught. So, total stress path we need to compute. It is fairly straightforward and it will be same as that of the drained stress path. So, delta T by delta S equal to 1, this we have already seen. So, it is a straight line at an inclination of 1:1 and this is u1. So, this is the total stress path. Now, for effective stress path we need to compute the pore water pressure expression, and that we have already seen. We have already got the pore water pressure expression. So, delta T dash. Now, we already know that delta T dash or delta T is equal to delta T dash, it is not getting influenced, but then still in this particular case I am just representing it as dash only to make you understand. Okay. So, delta T dash is equal to delta sigma A dash minus delta sigma R dash by 2. Substituting, so delta sigma A minus delta U minus delta sigma R minus delta U by 2. So, now we have the expression for delta U. So, substituting for delta sigma R equal to 0, because that is the condition, we have it is delta sigma A by 2, because minus delta U minus of minus is plus delta U. So, that gets cancelled. So, it will be delta sigma A by 2. Delta S dash is equal to delta sigma A dash plus delta sigma R dash by 2, substituting. So, in terms of total stress, and then you will get delta S dash is equal to delta sigma A by 2 minus delta U. Why? Because here it is minus of minus. So, it is minus 2 delta U by 2, that is minus delta U. So, delta S dash is equal to delta sigma A by 2 minus A into delta sigma A, because delta U is equal to A into delta sigma A, which we have already found out. Now, delta sigma A dash is equal to delta sigma A by 2 into 1 minus 2A. So, rearranging this. So, delta T dash upon delta S dash is equal to 1 by 1 minus 2A. Everything remains same as that of the previous derivation. The same we need to find out what is the slope. So, slope is 1 by 1 minus 2A and it is again a function of A. So, if A is considered constant, it will be a straight line. Now, you need to see that this particular line can vary with A and it can be of any slope in this direction. So, N dash, M dash, N dash gives the effective stress path when A is considered to be constant, and if A changes, then it is a nonlinear stress path. For a specific case in this particular exercise, if A is equal to 0.5, you will see that what happens, it becomes infinite. Delta T dash by delta S dash is equal to infinity. So, it will go in the upward direction. The slope of the effective stress path will be in the upward direction. In fact, these informations are very important when we try to understand the critical state soil mechanics. For NC, a typical A value will be 0.5, If you are representing the stress path in TSS dash plot, we know that it is moving in the upward direction. Similarly, for compression in QPP dash plot, it is one and the same, only thing is the expression changes. So, we are just trying to find out the expression, all other things remain same. So, P naught dash is equal to P naught minus U naught. So, this is the starting point. So, total stress path remains same. So, we can say that it is at an inclination of 3 because it is a compression stress path. Delta Q is equal to delta sigma A and delta P is equal to delta sigma A by 3. So, the slope will be 3 and this remains same as that of drained stress path. Now, for effective stress path, delta Q dash is equal to delta sigma A dash minus delta sigma R dash. Substituting for total stress in terms of total stress. So, we have delta Q dash is equal to delta sigma A minus delta U, minus of this becomes minus delta U plus delta U 0. So, that will be equal to delta sigma A. So, delta P dash is equal to, again substitute in terms of pore water pressure, delta P dash is equal to delta sigma A minus delta U plus 2 into minus delta U. So, that will become minus 3 delta U by 3 that goes. So, delta sigma A by 3 minus delta U. So, delta P dash is equal to delta sigma A by 3 minus substitute for delta U A delta sigma A. So, delta P dash is equal to delta sigma A by 3 1 minus 3 A. So, delta Q dash upon delta P dash is equal to 3 upon 1 minus 3 A. So, again if A is considered constant, it will be in this, this is only an example direction, it can be in any direction depending on A. So, M dash N dash is the effective stress path and if it is considered to be, A is considered to be varying, so then it becomes a non-linear stress path. Now, for example, if AF is equal to 0.5, then in this case you will have an inclination of minus 6. So, it will be even more steep. So, you will have the effective stress path. Now, what we have done for undrained compression, we have determined the effective stress path for all the 3 cases. Now, the compression, just like we discussed for drained stress path, the compression can also be brought about in another sequence. So, undrained compression test with constant axial total stress. So, that is represented by U2. Initial stress conditions are considered to be isotropic. So, it all remains same. Release of radial stress causes compression. So, this we know that when axial stress is kept constant, we need to release the radial stress so that there is a compression. So, that is what we are discussing now. So, release of radial stress causes compression. Again the starting point remains same. So, delta sigma A is equal to 0 and delta sigma R is equal to minus delta sigma R. Why? Because it is release. So, we know that TSP is same as that of the drained stress path and that is for constant sigma A, sigma R is reducing. So, it goes and meets the failure line. Let us presume in this particular case that there is no initial pore water pressure. So, U naught is equal to 0. So, what is the implication of this statement? The total stress path and the effective stress path, it starts at the same point. So, M equal to M dash. So, that is what it means. So, ESP and TSP will start at the same point. So, we have M dash. Now, what is the next procedure? We know that it is undrained. So, we need to have the pore water pressure either measured or estimated. So, let us estimate U based on Skempton's pore water pressure equation. Is it going to be same or different? It will definitely be different because it will be corresponding to radial stress variation. So, delta U, again the same procedure, it is written in terms of delta sigma R, delta sigma A B equal to 1. So, delta U is equal to delta sigma R, rearranging this, plus A into delta sigma A minus delta sigma R. So, delta U is equal to A into delta sigma A minus delta sigma R into 1 minus A. So, now U is delta sigma R into A minus 1. So, earlier the expression was different. Now, we need to find out what is the effective stress path. So, effective stress delta sigma A dash is delta sigma A minus delta U. Substitute for delta U. So, that will be delta sigma A is already 0 because that is the condition what we are dealing with. So, minus delta sigma R A minus 1. Delta sigma A dash is equal to delta sigma R into 1 minus A. And delta sigma R dash is equal to minus delta sigma R because it is minus and minus delta U. So, delta sigma R dash is equal to minus delta sigma R, substituting for delta U is minus delta sigma R A minus 1. So, delta sigma R dash is equal to delta sigma R into minus 1 minus A plus 1. So, this minus plus 1 goes away. So, it gives minus A into delta sigma R. So, we will take the slope delta sigma A dash upon delta sigma R dash is equal to minus 1 minus A by A. Now, have you seen this expression before? Yes, we have seen, because the slope of the effective stress path remains same as in the previous case, even though the sequence of loading has changed. Definitely it has impacted the determination of pore water pressure. The expressions were different, but the slope is going to be same. So, whatever be the manner in which the compression has been done or performed, the effective stress path slope is same. So, that is a typical example wherein there is a slope, and if it is A is varying, then it will be non-linear. So, M dash N dash is the effective stress path. For both cases of compression, the slope of effective stress path, this expression remains the same. Same thing we need to repeat with TSS dash. So, it is clear now, since the slope for sigma A sigma R dash plot effective stress path was same in both the cases of compression, we know that it is going to be same for TSS dash and QPP dash. So, let us see how and whether it is okay or not. So, TSP is delta T delta sigma R by 2 minus delta sigma R by 2, because that is the condition. So, delta T by delta is equal to minus 1. This remains same as that of our drained stress path. So, U2 is in this direction. So, this is the total stress path. Effective stress path, the initial point is same because U naught equal to 0, delta T dash is equal to delta sigma A dash minus delta sigma R dash by 2. Substitute in terms of total stress, yes, delta U, the expression is known. So, we have substituting for delta sigma A equal to 0, we get minus delta U minus. So, that will become plus delta sigma R, and this will become plus delta U, that gets cancelled off. So, delta T dash is equal to delta sigma R by 2, and delta sigma S dash is equal to delta sigma A dash plus delta sigma R dash by 2. Substituting it for in terms of delta U, we have delta S dash is equal to 0 minus delta U plus, that is minus delta sigma R minus delta U by 2. So, that will give minus delta sigma R by 2 minus delta U. Substitute for delta U. So, if we substitute for delta U, so then we will get delta S dash is equal to minus delta sigma R by 2 minus delta U. So, delta S dash is equal to minus of delta sigma R by 2 minus A minus 1 delta sigma R. So, this is the expression for delta U. So, delta S dash is equal to delta sigma R by 2 into minus 1 minus 2A plus 2. So, that is 1 minus 2A. So, delta T dash upon delta S dash is equal to 1 by 1 minus 2A is the same expression. So, this is the effective stress path, and if it is varying, then non-linear. So, similarly with QPP dash, we will quickly glance through all the steps remain same. So, TSP is equal to delta Q is equal to delta sigma r. So, we have delta P is equal to minus 2 delta sigma r by 3. So, that gives the slope of minus 3 by 2 is the total stress path, and effective stress path starting same, again the same procedure, we get delta Q dash is equal to delta sigma r, and delta P dash is equal to delta sigma A dash plus 2 delta sigma r dash by 3, and delta sigma A minus delta u plus 2 into delta sigma r minus delta u by 3. So, delta P dash is equal to 0 minus delta u plus 2 into minus delta sigma r minus delta u, and that is equal to minus 2 delta sigma r by 3 minus delta u. So, delta u gets substituted. So, delta P dash is equal to delta sigma r by 3 into 1 minus 3a, and the slope is 3 by 1 minus 3a, and that remains same. This is the m dash, n dash is the ESP and the nonlinear variation. So, in all the 3 cases we have got the slope of the effective stress path same in both the cases of compression. In both ways of compression it is same. Now, obviously the curiosity arises whether this will be true for extension, because we have discussed 4 cases in undrained as in the case of drained stress path. So, is it going to be same? So, let us see the case for just the plot of sigma A sigma r dash. What will be the slope of undrained effective stress path for both the cases of extension? So, undrained extension test with constant radial total stress. So, we know that if it has to be extension, then the axial stress has to be released. So, minus delta sigma A, and delta sigma r equal to 0. So, delta u is equal to b into delta sigma r plus a b delta sigma A minus delta sigma r. So, that gives, substituting delta sigma r equal to 0, we have delta u is equal to minus a delta sigma A. Now, we can find out delta sigma A dash. Substituting for delta u, we get delta sigma A dash is equal to delta sigma A into a minus 1, and delta sigma r dash is equal to 0 minus delta u, that gives delta sigma r dash is equal to a into delta sigma A. So, we are substituting it for the pore water pressure, and that gives again delta sigma A dash upon delta sigma r dash. If you rearrange, it will give minus 1 minus a upon a. So, the same slope as in the case of compression. So, even the extension case, the slope is going to be same and it is unique. Now, the 4th case is undrained extension test with constant axial total stress. So, we need to create extension. If it is axial total stress, then delta sigma A equal to 0. Then if extension has to be created, then it has to be increase in the radial stress, so that it is a kind of squeezing effect, delta sigma r. Substituting now is the same procedure, delta u is equal to delta sigma r 1 minus a, delta sigma A dash we can find out, that is 0 minus delta sigma r 1 minus a. So, delta sigma A dash is equal to minus delta sigma r into 1 minus a. Delta sigma r dash is equal to delta sigma r minus delta sigma r into 1 minus a, and that will give delta sigma r dash is equal to a delta sigma r. So, delta sigma A dash upon delta sigma r dash is equal to minus 1 minus a by a, these are identical. So, whatever be the manner in which the stresses are varying, if it is compression or extension, the effective stress path expression is unique. So, different TSPs and unique ESP. So, we have different TSP, and this TSP variations for different cases of compression and extension. We have seen that this is very much similar to that of the drained stress path, but for all these TSPs we have the unique ESP. This is just an example, this particular slope. So, it is unique ESP, that is what we have understood from our previous discussion. So, A value influence on ESP, how A is going to change the ESP. So, this is a TSS dash plot, the starting point M. So, this is the TSP, for a typical case of compression and extension. Now, if A is equal to 0.5 in TSS dash, we know that it is infinity, so it moves in the vertical direction. Now, for A equal to minus 0.15, that is, this has A minus 0.15 means it refers to a heavily over consolidated soil. So, in that case, the effective stress path moves towards in this direction, that is in the rightward direction, and touches the failure envelope. Now, if it is different value other than A, then we will see that this effective stress path will move leftwards. So, if it is a kind of, so these are the different cases of how the A value would influence the effective stress path. So, more or less we have discussed all the different aspects of stress path for undrained testing. So, let us summarize today's lecture. So, triaxial undrained stress paths are discussed. ESP and TSP is separated by pore water pressure developed during shearing. ESP in undrained triaxial test is unique for identical soil specimen and initial state. ESP is same irrespective of the manner in which shearing is imposed, whether it is compression or extension mode. In all the cases we have seen that the expression for effective stress path remains the same. ESP is governed by Skempton's A parameter and exhibit nonlinear variation during shearing, and ESP is assumed to be straight line variation from starting to failure by assuming A value to be constant. In sigma A dash, sigma R dash stress path plot, the slope of undrained effective stress path is minus of 1 minus A by A. Now, in TSS dash plot it is 1 by 1 minus 2A, and in QPP dash plot it is 3 upon 1 minus 3A. So, these expressions are unique. So, in undrained test, failure is entirely defined by ESP when it approaches the failure line. So, we do not have anything to do with the total stress path, and this particular aspect will become very clear as we move further. So, that is all for this lecture. Thank you.